person. Yeah, Quanzhou, great.
Great. So hi everyone, my name is Quanzhou Li, and I'm going to present the project we call it IOS, Imitation from Observation at Scale via Disentangled Latent-Based Learning. So first of all, I'm going to do a very quick review of imitation learning. So imitation learning is a learning method that uses demonstrations generated by experts. The experts can be humans or RL agents to learn a policy so that the learner can use this learned policy to mimic the behaviors of the expert. You can see the left image shows the demonstrations, and the demonstrations are basically sequences of state and action pairs. So the algorithm uses sequences of state and action pairs to learn a policy that the learner, the agent, can execute. An imitation from observation is a method that is very similar to imitation learning. But instead of using state and action pairs, imitation from observation only uses the states as demonstrations. So because of the difference of the two methods, imitation learning typically requires the expert to be the same to the learner, since the expert and the learner should share the same action space. But for imitation from observation, sometimes the expert can be different from the learner, because you don't need to worry about the action space and for the observation. So for example, if the observation are both images, then it will be simpler to transfer between the two domains. The next is our motivation to do this project. Recently, the robot learning community has started a thread in large-scale imitation learning research. Large-scale dataset like RobotTurk has accelerated the process in the field of policy learning. However, imitation from observation at scale is still a problem that has not been discussed much. So nowadays, the size of human-generated data, like images and videos, has grown exponentially. And people can easily get access to this data through the internet. And they can also produce images and videos by themselves very easily. So compared with collecting imitation learning data sets through teleoperation or kinesthetic teaching, this way of producing videos and images is way easier, and it extends the imitation learning to larger scale by allowing learners to learn from these videos. But this also faces several challenges. So the first one is that the expert and learner may be different in morphology. So for example, if you want to teach a robot to do a task like cooking, and you may not be able to find videos that the robot cooking on the internet. So basically, the easiest videos you can find is human cooking. So you may want to use human cooking videos to teach a robot to cook. Then you have to deal with this different morphology problem. And the second is that the demonstrations are image-based, and typically image is a pretty high dimension vector, and doing reinforcement learning with high dimension observation is generally hard. And since you're only using images and videos to do this imitation learning, it's state only, and you have no access to the actions that people made in the videos. And also the demonstrations may be diverse. So for a single task, there might be different ways to solve this task. And the demonstrations shown in the videos may be suboptimal. So these are the challenges we may face. And in this project, our plan is to achieve learning from an expert different in morphology from the learner in simulation. And we may apply this to real-world robot in the future. So here we have a robot domain. The expert demonstrations are in the robot domain, and the demonstrations are basically the images of the robot. And the other is a learner domain with learner observations. The observations are also images. So our objective here is to first learn a shared latent space of the two domains, which means to learn an encoder to encode images from the two domains to a latent space. The latent space is supposed to be domain invariant, so it only contains the shared features across the domains. And the second objective is to learn a policy for the learner. So at training time, we use the encoder learned from the first step to encode the expert demonstration to the latent space. and use this latent code to do the learning. And at testing time, we also first encode the observations and then use the latent code to execute the policy that learned from the training. Our work is based on a previous work called AVID. So in their job, they basically use the CycleGAN to directly translate the images of instructors to robots and use the translated images as demonstrations to do imitation learning. So the problem of this method is that learning directly from the translated images, translated videos, the translated images is susceptible to inaccuracies due to the artifacts caused by translation. And also, as I stated before, image space is a pretty high dimension space, and reinforcement learning with high dimension observations can be very hard. So in order to tackle these problems, we use a MUNIT-like image-to-image translation model. So MUNIT and DRIT are models of image-to-image translation that separate images to domain-specific spaces and the domain invariant space. We basically separate one image into a content code and a style code, and use this content code and style code to reconstruct the image. And the content code is supposed to be shared across the corresponding images from different domains. So if two images from two domains are corresponded, they should have the same content code. That is the shared latent space assumption that we also propose in our project. It basically says the content, so one image should be able to separate into a style code and a content code, and the content code should be shared across domains. And this is the image translation results of our model. So as you can see, the first line is the input images, and the third line is the output images. So the translated images, and the other are reconstructed images. We're not directly using these images to do the imitation learning. Instead, we use the encoder trained by this model to encode these images to a latent space and use the content code to do the imitation learning. As you can see, the general visual quality of this translation model is good, but sometimes it may suffer the object missing problem. So after translation, the object may be missing because of the size of the object is pretty small in terms of the whole image. So in order to tackle this problem, we're also working on incorporating an object detector to this model to emphasize the existence of the object. So the result is the object detection we made with detection 2, and we're currently working on incorporating these two to the same model. And so far, I've talked about the upstream parts of the project. And for the downstream part, we basically use a RL to first train expert in simulation and use this expert to generate demonstrations. And then we use a random policy on this learner to also generate some images by executing this random policy. And then we use the images generated by the learner and the generated demonstrations to train the image-to-image translation model. And then we use this trained encoder to do the imitation from observation learning. So for the imitation from observation part, we use GAFO, which is a state-of-the-art image from observation algorithm. And for GAFO, we just leverage the demonstrations to mimic the behaviors of the expert through learning in the latent space. So by using this content code, encoded by the content code. So for the future work, first, we can extend this image-to-image translation part to a multi-domain setting. So instead of doing this for 2 domains, we can do for 3 or 4 multiple domains. And also, we can apply hierarchical imitation learning to solve longer horizon tasks. So currently, we're doing with some very simple tasks like robot reaching and robot lifting, and even pick and place can be considered as a hard task for now. So with hierarchical imitation learning, we may be able to solve long horizon tasks, so harder tasks and more complicated tasks. And also we can consider implementing this method in a real-world robot system. So we can use this to in a real-world setting to learn from real human videos and guide the robot to do something. And that's all. Thanks for listening.
Thanks. Do we have questions? I don't see any questions in the chat box. No raised hands either. So let's then move on to our. Okay, so Stephen says he has a question. Stephen,
Yep.
go ahead.
Yeah, can I just talk if that's okay?
Hello, Stephen. Can
Yeah,
you
hey.
unmute yourself? Yeah, you're unmuted.
Can you guys hear me? Yeah.
Yeah, we do.
Okay, yeah, so thanks for the presentation. I just wanted to check my understanding to see if I'm getting this. So basically what you do is instead of standard imitation learning, you're just learning from trajectories like expert demonstrations in the actual space. What you're doing is you're stacking an autoencoder like on top of the images that you observe. So you translate the images into the latent space, and then you apply the standard like RL imitation learning algorithms on top of that latent space. Is that sort of what's going on here?
Yeah, so basically we just train an encoder and you use the encoder to encode the images. So we're not directly using the images, but use the encoded vector. Yep.
Yes, the way you train the encoder is like a standard like autoencoder like reconstruction loss. That's kind of how you would do it.
Yeah, so basically we propose a loss to keep the content code same across the domains, and then we also reconstruct the images and there's a loss to calculate the difference of the reconstructed images and the original images.
Wait, so maybe I missed this part of the presentation because I remember you talked about the content code, but could you just explain that again? Like, what is the content code and how does that work?
So one image is separated into content code and style code. The content code is domain invariant, so the content code is shared among the corresponding images. So for example, we want to transfer a cat into a dog, and the cat image and the dog image are two corresponding images, and they should have the same content code, and they may have different style code. So the style code is domain specific, and the content code is domain invariant.
How do you determine what the content code is?
Determine so basically the content code contains the shared features of the two domains, so the shared information of the two domains. So we actually extract the shared information of the two domains and a domain specific information, and we separate this two information, and we only use this the shared features, this shared information across the two domains.
So is it like learned automatically then? Or it's like learned within your model?
Yeah, okay, that's unsupervised learning method.
Oh, okay, I see. Okay.
Yep.
Okay, thanks.
All right then. Thank you.